Most mechanical engineers graduate without ever studying the joints that make real product and hardware design possible. We're taught things like stress-strain curves and the Bernoulli equation and how to use CAD software, but not the designs that industry and life-changing products actually depend on. The truth is, a small set of deceptively simple joints quietly determine product performance and power everything imaginable, from precision robotics and spacecraft to manufacturing and transportation. If you understand them deeply, far beyond textbook physics, then you immediately become a better designer. So in this video, we'll examine 8 of the most essential mechanical joints that have had measurable global impact. For each one, I'll break down the physics and engineering principles behind it, the modern applications where it remains essential, and how modeling and building it will elevate the quality of every mechanical system you design. The first and most misunderstood is the preloaded bolted joint. A bolt isn't simply a pin that holds parts together through friction. I like to think of it as a very stiff, high-strength spring. The core physics begins with the concept of preload, which is the initial tension created when you torque a bolt. When tightening, you're elastically stretching the bolt shank and compressing the joint members. This creates a clamping force. This is critical for fatigue life. In high cycle applications like internal combustion engines or aircraft wings, if a bolt feels the full swing of every load cycle, it will eventually fail via fatigue. By maintaining a high preload, the bolt experiences a nearly constant stress state, shielding it from fatigue. The design challenge here involves calculating the torque-tension relationship, accounting for the K factor or friction coefficient of the threads. Too much friction and you break the bolt before reaching preload. Too little and the bolt vibrates loose. Bolted joints appear everywhere, from engine cylinder heads and aircraft structures to pressure vessel flanges and machine tool frames. A potential project could be to design a test rig to measure bolt creep or relaxation. Model a joint in CAD, calculate the required torque to achieve 70% of the bolt's yield strength, and use a load cell or ultrasonic bolt tension monitor to see how much clamping force is lost over 24 hours as the surfaces settle. Second is the Revolute Joint, which is the foundation of mechanical motion. It allows rotation about a single axis while constraining all other degrees of freedom. Every linkage, hinge, engine, and robotic arm depends on Revolute joints. In reality, it's one of the most common sources of wear, friction, and failure. So the moment a Revolute joint carries load, it becomes a contact mechanics problem. Journal bearings, rolling element bearings, bushings, and plain pins all behave very differently under speed, load, and contamination. Designing for clearance is critical. Too tight and the joint will bind under misalignment or thermal expansion. Too loose and you'll experience backlash, vibration, and fretting wear. You'll find Revolute joints in door hinges, suspension linkages, robotic arms, and engine components like piston wrist pins and connecting rods. A useful project could be to build the same linkage using 2 different Revolute joint implementations, for example, a bronze bushing versus a ball bearing, and measure things like friction, backlash, and wear over repeated cycles. Third on the list is the Flexure Joint. Flexure joints replace contact with elastic deformation. Instead of allowing motion through rolling or sliding, Flexure joints allow motion by bending material within its elastic limit. This single idea changes everything because they exhibit zero backlash, require no lubrication, produce no wear debris, and offer exceptional repeatability. Their behavior is governed entirely by material properties and geometry. However, the engineering challenge here is strain-based design. Stress concentrations, fatigue life, and allowable rotation are controlled by thickness, length, fillet radius, and material choice. Living hinges is a type of flexure joint that is often mass-produced. They are compliant and made of nothing but thin sections of the material itself and connect 2 rigid parts, allowing them to fold. They rely on molecular alignment during molding and controlled bending strain to survive millions of cycles. As a mechanical engineer, the challenge is designing the geometry of the flexure. If the hinge is too thick, it will crack, and if it's too thin, it won't provide enough support. Flexure joints are used in camera modules, MEMS sensors, optical assemblies, and smartphone camera autofocus systems and laptop trackpads. A great project could be to design a 3D printed enclosure that uses surfaces a living hinge, simulate stress and fatigue life, and then validate it experimentally. You'll need to experiment with layer orientation. If you print the hinge in the wrong direction, the layers will delaminate. This teaches you about material science, geometry, and manufacturing constraints. Fourth is the kinematic coupling. A kinematic coupling uses exactly 6 points of contact to constrain the 6 degrees of freedom of a part. The classic Maxwell mount uses 3 spheres resting in 3 V-grooves oriented toward a common center. Each contact point removes 1 degree of freedom. It's also thermally stable due to symmetry because the curved surfaces can expand or contract in unison in the V-grooves. The Kelvin coupling, on the other hand, consists of 3 spherical surfaces that rest on a concave tetrahedron, a V-groove pointing towards the tetrahedron, and a flat plate. The tetrahedron provides 3 contact points, the V-groove 2, and the flat plate 1, for a total of 6 contact points. The center of rotation is located at the tetrahedron, so it suffers from contact stress problems in high load applications. Kinematic couplings are mostly found in high precision equipment like semiconductor machines, optical systems, and scientific instruments. A good project could be to build a kinematic mount using steel balls and machine grooves, then measure positional repeatability after dozens of assembly cycles. Fifth is the interference fit. This is a joint that requires no fasteners, adhesives, or welds. It relies entirely on elastic deformation. By designing a shaft slightly larger than its mating hole, assembly creates hoop stress and normal force at the interface. This frictional force can transmit enormous torque, often more reliably than keyed or bolted joints. Shrink fitting uses thermal expansion to make assembly possible. Heating the hub or cooling the shaft allows parts to slide together. Interference fits are used in railway axles, bearing seats, turbine components, and high-power rotating machinery. The engineering challenge here lies in calculating the allowable interference using thick-walled cylinder theory. Too much interference and you'll exceed the yield stress of the material and experience cracking. Too little and the joint slips. A classic way to explore interference fits is with a steel shaft and aluminum housing. By freezing the shaft and heating the housing, you can assemble them easily, then measure the breakaway force with a hydraulic press or load cell. Compare this to your theoretical calculations. Sixth is the spline joint. A spline uses multiple teeth to transmit torque between a shaft and a hub. By distributing load across many contact surfaces, splines dramatically reduce stress concentrations compared to keys or pins, where a small piece of metal bears the entire load. In a spline, the surface area for force transmission increases by 500% or more. Involute splines are particularly clever because they use the same geometry as gear teeth, allowing them to self-center under load and maintain uniform stress distribution across teeth. Splines are foundational to automotive drivetrains, jet engines, and industrial gearboxes. For a project, you can model an involute spline in CAD and perform FEA analysis between a single keyway and a 10-tooth spline under identical torque. Visualize the stress risers and see how the spline smooths out the load path. At number 7, we have the snap fit. It's a temporary mechanism that transforms into a permanent joint upon engagement. Analysis is governed by beam theory. A snap fit is essentially a cantilever beam with a hook at the end. As you push the parts together, the beam deflects and then snaps back into a neutral position once the hook clears the undercut. The engineering challenge is ensuring the strain during deflection doesn't exceed the proportional limit of the plastic. If you overstrain it, the snap fit simply turns white and loses its strength, or simply snaps off. Mechanical engineers use formulas that account for the taper of the beam and the friction angle of the lead-in and return faces. This determines how much force it takes to push it together versus how much force it takes to pull it apart. Snap fits are found throughout consumer products, especially in plastic housings for electronics, appliances, and automotive interiors. A project could be to design a snap fit enclosure for a PCB. Calculate the deflection required and the resulting strain based on your material's datasheet. 3D print it and test the separation force. Now, before we continue, one of my favorite platforms that helped me become a much stronger problem solver and master essential math, physics, and engineering principles was Brilliant, the sponsor of today's video. Brilliant helps you excel in math, physics, computer science, data analysis, and AI with visual interactive problem solving and personalized practice. Brilliant is highly effective because you learn through active problem solving, a method proven to be far more powerful than watching lectures or videos. It has a perfect mix of interactive problems and motivating challenges and encourages you to keep making progress. Brilliant starts you at the right level based on your background, designs practice sets and reviews personalized for you, and helps you advance at your ideal pace. Brilliant is crafted by award-winning teachers, researchers, and professionals from MIT, Harvard, Stanford, Caltech, Google, and more, so you learn from the best. With Brilliant, you don't just memorize formulas. You get hands-on with concepts until they make sense and develop the intuition and problem-solving skills to figure things out on your own. One of my favorites is Brilliant's scientific thinking course that teaches you how to think like an engineer with lessons in gear systems, physics, circuits, and more. To learn for free on Brilliant for a full 30 days, go to brilliant.org/engineeringgonewild, scan the QR code on screen, or click on the link in the description below. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Lastly, at number 8 are the universal and constant velocity joints. It allows torque transmission between angle shafts, but it does not transmit constant velocity. When the input and output shafts are at an angle, the output shaft does not rotate at a steady speed. Instead, it accelerates and decelerates twice per revolution, even if the input speed is perfectly constant. This is known as fluctuating angular velocity. These speed fluctuations destroy bearings, loosen fasteners, and generate noise. Constant velocity joints solve this issue. By keeping all the contact points in a hemokinetic plane, the input speed perfectly matches the output speed regardless of the angle. Double cardan joints have a centering element connecting two universal joints in series that maintain equal angles and proper phasing between the driven and driving shafts, so the velocity errors cancel. Another notable constant velocity joint is the Chepa joint, which uses 6 steel balls running in curved grooves between an inner star and an outer spherical housing. The geometry forces the balls to lie in the plane that bisects the angle between the shafts, which guarantees that the output rotates at the same speed as the input. This allows large articulation angles over 45 degrees while transmitting smooth torque. While there are many other constant velocity joint variants optimized for packaging, plunge, and load capacity, they all exist to solve the same fundamental velocity problem. Constant velocity joints are found in automotive drivetrains, especially in front-wheel drive, all-wheel drive, and independent suspension vehicles. A very cool project could be to build a simple test rig with 2 shafts and a single universal joint. Use a high-speed camera or an encoder to plot the output velocity at a 20-degree angle. Then reconfigure the rig into a phased double cardan setup and observe how the output velocity graph flattens out. These joints determine a very important principle. While they often disappear into the background of a design, joints largely determine how loads are transferred, how motion is constrained, and where failure ultimately occurs. Based on my experience working across consumer electronics, tech, and automotive products, the best mechanical engineers are the ones who treat joints as first-class design elements. They understand where compliance is intentional, where rigidity is critical, how assembly affects performance, and how wear tolerance stack up and fatigue accumulate over time. Mastering these joint designs not only improves individual components, but also sharpens your system-level intuition and directly impacts reliability, manufacturability, and long-term product performance. Alright guys, that's it for today. As always, thank you so much for watching. If you found this video helpful, be sure to check out my video here where I talk about the mechanisms that every mechanical engineer should know, and I'll see you in the next one. Peace.